All right, let's talk about recursion. In the world of computer programming, there are very few concepts that are as notoriously mind-bending yet wildly elegant as this one. If your brain has ever felt like it was tying itself in a knot trying to figure out how a function can run inside itself without literally breaking the universe, you are in exactly the right place. In today's explainer, we're deconstructing recursion from the ground up, turning this abstract mystery into a totally practical tool for your programming toolkit.
Here is what we're covering in the explainer today. 1. What is recursion? 2. Anatomy of a function. 3. Tracing the call stack. 4. Recursion versus iteration. And 5. Common mistakes. Let's get right to it.
Section 1. What exactly is recursion?
To kick things off, we really have to pose the fundamental question at the heart of all this. What actually happens when a function calls itself? I mean, it sounds like a total paradox, right? Kind of like holding a mirror up to another mirror. But instead of just creating this infinite chaotic loop of reflections, in programming, it's actually a very deliberate, calculated journey inward.
Here is the absolute core definition you need to remember. Recursion is simply a process where a function tackles a massive problem by calling itself on a smaller, similar version of that exact same problem. It literally chips away at the task. Every single time the function loops back and calls itself, it is taking one step closer to a known stopping point.
Moving on to Section 2, the anatomy of a recursive function.
Picture a standard countdown sequence. You hand the function a number, and it instantly has a built-in decision to make. If it hits 0, bam, it triggers its stopping point, say printing liftoff. But if it's not 0 yet, it prints the number, and then this is where the magic happens. It calls itself all over again, just with the next smallest number. Now, that sequence works seamlessly because it has the two absolute non-negotiables of any recursive algorithm. First up, the base case. That is your stopping point. Without it, the function just keeps calling itself forever until it completely crashes your system. Second, you have the recursive case. This is where the function actually calls itself using a slightly smaller or simpler input, pushing the whole process inevitably closer to that base case.
Okay, Section 3, Tracing the Call Stack. Let's trace this out. Imagine we run our program and pass in the number 3. The computer checks, is 3 equal to 0? Nope. So it prints 3 and fires off a completely new call for 2. Then that call checks its base case, prints 2, and calls 1. This repeats safely until we finally call 0. Boom! The 0 condition is met, the base case triggers, it prints liftoff, and the whole sequence stops. The input safely shrank right down until it hit the brakes.
Now, here's where things get really fascinating. We need to talk about how recursion handles returning actual values, rather than just printing text. Because not all recursive functions just print strings to a screen. Many of them, like calculating mathematical factorials, actually need to pass data back. The secret sauce here is that each individual call pauses and waits for the smaller call to finish its job before combining that new answer with its own value.
Let's visualize this with a factorial calculation. Say we want the factorial of 4. The function doesn't just instantly know the answer. All it knows is that the answer is 4 multiplied by the factorial of 3. So the first call just goes to sleep and waits. Then the factorial of 3 does the exact same thing, waiting on 2. This bubbles all the way down until it hits the base case of 1, which simply returns 1. And then a massive chain reaction fires backward. The 1 gets passed up to multiply by 2, which passes up to multiply by 3, which passes up to multiply by 4, finally giving us our answer, 24.
But listen, all that waiting around absolutely comes at a cost, and it happens inside what we call the call stack. Think of it like a giant stack of dirty plates. You literally cannot reach the plate at the very bottom until you've cleared off every single plate stacked on top of it. Every recursive call eats up your computer's memory. When the factorial of 4 is waiting, it stays parked right at the bottom of the stack. Then 3 sits on top of it, and so on. They have to return in reverse order, from the top down. This is critical to remember. Unfinished calls use extra memory. If your base case is wrong, your stack is going to grow until it literally overflows, handing you the dreaded recursion depth error.
All right, Section 4, Recursion versus Iteration.
This brilliantly illustrates the divide between the two. On one side, we have a recursive function to sum up numbers. On the other, we have an iterative for loop doing the exact same task. They both cross the exact same finish line, but they take fundamentally different roads to get there. If we compare their traits side by side, the trade-offs are super clear. Iteration uses a standard loop structure,
which generally demands much lower memory overhead. And honestly, it's often easier for beginners to trace. Recursion, on the other hand, calls itself. While it can demand a higher memory cost because of that call stack we just talked about, it is incredibly elegant. When a problem naturally breaks down into smaller subproblems, recursive code can be highly readable and cleanly match the logic of the problem itself. Both have their risks, though. An iterative loop can run infinitely if a condition never changes, while recursion can fail catastrophically if that base case is missing.
Which brings us to Section 5, Common Recursion Mistakes.
Welcome to the dark side of recursion. Take a look at this humorously flawed logic. We're calling a function with n plus 1. If your goal is to count down to 0, but you start at 5 and your next call is 6, then 7. You were literally counting in the wrong direction. The input just gets larger, spiraling endlessly away from the base case. Total disaster.
And that example perfectly highlights the most frequent errors. 1. Having absolutely no base case at all. 2. Having an unreachable base case like counting away from it. 3. Forgetting your return statement, which means the recursion runs, but the final answer never gets passed back down the stack. 4. Changing the input incorrectly, maybe skipping values entirely. And 5. Just good old-fashioned human error. We trace only the very first call in our head, completely forgetting the massive pile of calls waiting in the stack behind it.
Finally, Section 6. Let's look at the key takeaways.
Consider this your concrete recursion toolkit. Whenever you are reading, writing, or trying to trace a recursive algorithm, ask yourself these 4 golden quick-check questions. First, what is the base case? Second, exactly how does the input get smaller to actually approach that base case? Third, what value or output is being produced in passback? And fourth, are you absolutely certain the algorithm always stops? Mastering these 4 questions empowers you to trace almost any simple recursive algorithm successfully.
Which leaves us with one final thought to ponder before you jump back into your code editor. Now that you understand the elegance of breaking a problem down, the hidden power of the call stack, and the absolutely critical importance of the base case, when you face your next complex programming challenge, will you rely on a safe, standard loop, or are you brave enough to recurse? Keep building, and we'll see you in the next explainer.